So 8 goes into 72 9 times. Okay. Then you factor those two numbers down. 8 is 4 and 2. 4 can be factored. Not to 4. 2 and 2. 9 can be factored to 3 and 3. And then you're looking for what kind of pattern here? Doubles, right? You're looking for pairs of numbers. And so I have 2 2s right here, 2 3s right here. What that means I'm going to do is pull 1 2 outside the radical. I'm going to pull 1 3 outside the radical. And what am I going to do with those two numbers? Multiply. And then what's left over? This 2 right here. So this is going to be 6 radical 2. This is generally how my students go about the radicals. Okay? What I like to do, and what you'll see me do during the lessons, is look for the biggest perfect square that goes in. So if I was approaching this problem, I would notice that 2 goes in 36 times, and I like to rewrite the radical factors horizontally, like this, under the radical. It just helps me keep things in a better order and for the students to see, because this way, I notice what happens. A lot of students forget about this little lone 2 right here. So if I write it out horizontally, it keeps things from getting lost. But you don't have to do that. You do whatever way works for you. So right here, I would say, okay, the square root of 36 is 6, and I would bring that outside and have 6 radical 2. All right? So you can do this way, where you just factor down to perfect squares. You can do this way, where you factor all the way down and then look for pairs. Whatever works best for you. But generally, what I'm going to do is this way. It's good for you to see it, whether it's your preferred way or not. Okay? So what you've grabbed when you've walked in is you have a calendar and you have today's notes. Tell me, according to your calendar, when your quiz is. Friday, okay? And when is your test? 24th, 2 weeks from tomorrow. So here's what's going on this unit. Next week, we start factoring, okay? We're solving quadratics with factoring. The reason why this week we're talking about complex numbers, which are imaginary numbers, or include imaginary numbers, is because when we get to the factoring part, we want to be able to use the skills from this week in our factoring later. So no factoring just yet. We're going to be talking about complex numbers this week. So if you go to your notes, the very top left corner, I want you to highlight or circle or somehow mark as important this thing right here. It says, recall that I equals the square root of negative 1. You may not feel that that's a recall. You may not ever remember having seen that before, but you have, I promise. Anytime, so we just simplified the square root of 72, right? This tip right here that we just highlighted is something we'll use if we're taking the square root and there's a negative underneath. Our warm up didn't have a negative, but if we do, we're going to use this. Anytime you see a negative 1, the square root of it simplifies to I. And just as a brief little tiny baby history lesson, the reason why this is even a thing is because somewhere along the way, when mathematicians were trying to solve some fancy problems, they would get to where they were trying to take the square root of a negative number. But in the real world, that doesn't exist. Like when we talked about classifying numbers, and I said like, oh, imagine cavemen and their rocks, they're counting 1, 2, 3, 4. Those were natural numbers, right? Negative numbers are abstract, but we still kind of understand them, okay? This is a whole other level of abstractness. But what mathematicians do sometimes is they just say, okay, we need a solution to the problem of the square root of a negative. And so we're just going to call it I, and then we're all going to get on board and move on and do more fancy math with that information. They just make it true, and all agree that it's true. That way they can keep doing their math. And so the reason why this is here is because imagine that you have, like if I asked you, what's the square root of 9? What would you tell me? 3, because 3 times 3 is 9. But if I asked you what times itself gives me negative 1, you wouldn't be able to come up with anything. Because a positive number times itself has what sign? a negative number times itself has what sign? Positive. Negative times negative is positive. And so this was the stumbling block. Well, there's no two numbers multiplied that will give you a negative. And so we just say, well, you know what, we're just going to call it I. And this is an imaginary number, right? It's not part of the real numbers. So that's why we're talking about that today. So this basically says if the value under the radical is negative, place an I outside to rewrite it as a positive. Step 2, find the prime factorization using either a factor tree, which we did in the warm-up, or upside down division, which I think is like that birthday cake looking method. 3, every pair of the same factor under the radical should be replaced by one of that in front, which we talked about in the warm-up. And then you multiply the factors that are in front, and you remultiply the factors that are left over underneath, and then simplify if possible. So all that's just the basic steps for radicals, and we're going to be working with it a lot today. So we've got this first set of examples. A is the square root of negative 81. I like to think about that as two different numbers under there. Negative 1 times 81. I'm going to take the square root of those separately. What did we just say that we're going to use for the square root of negative 1? I. So it comes out as I. And what's the square root of 81? Okay, when you pull things out of the radical, they get what back together? What operation? Multiplied. So that's going to be 9i. And then what's left under the radical? Nothing. So the radical goes away. If you've got nothing left, don't force the radical there. It's okay that it sometimes just completely goes away. The second one, the square root of 98. 98 is not a perfect square. I will factor this as 2 times 49. So then I have this, square root of 2 times 49. Which one of those is a perfect square? What is the square root of 49? 7. So the 7 comes out. The 2 stays under because it's not perfect. Sorry, 2, you're not perfect. You try C. Anything you pull out of the radical to be multiplied by the 3 up front. That's okay. It just means you need some extra practice. So you either get with me before or after school, go on YouTube, go on Khan Academy. I do not mind sitting with you and just doing practice problems, okay? It might just be something you need refreshed on. So when I do 144, 144 is a perfect square. What's the square root of 144? 12, right? So if you can recognize your perfect squares, you save yourself some math too, because you didn't actually have to do the factor tree. So two things going on. The square root of the negative 1 is I. Square root of 144 is 12. I saw this common wrong answer. Someone tell me what this person is kind of right, but kind of wrong. What are they forgetting to do? Times the 3 out front, right? That was about a third of you gave me 12i. Don't forget about the 3 up front. So it's really 3 times this, so 36i. For the last one, it's not a perfect square, so you will need some kind of factoring. But this negative that goes out front, that happens at the end of all your other work. You may not, right here, do plus plus. They're not being multiplied because the negative underneath is part of the radical. So sort of, I would recommend just sort of doing that in parentheses to tell yourself to do this first, do that negative on the outside last. So go ahead and try that one. Negative, what's the perfect square that goes into 75? 25. So this is 3 times 25. If you factor treated out, you wouldn't have 25, you'd have 5 and 5. But for what do you do with a pair of 5s? You pull out 1 5. So either way, you're pulling out 1 5, because the square root of 25 is 5. I feel like if I say 5 one more time, I'm going to scream. Negative 1 right there is I. So then here's your answer without me saying that number again. Okay. Questions or concerns before we move from this slide? All right. Try A and B. Don't try C and D unless you're feeling particularly ninja-like. That's some whole other level. So just wait. Do A and B, please. Just at a minimum, do A and B. They can't be factored. What do we call numbers that can't be factored? Prime. They're prime numbers. But we can take care of what thing? The negative under the radical. Okay, comes out as I. So this is I rad 17, I rad 53. Okay. So those could not be factored treed because they're prime. Okay. So for the next two, you'll notice that those are fractions under a radical. Those are different from this over here in our I will statement, which is, it is a fraction, but there's two terms on top. So we're going to deal with that one differently. For these, how I want you to begin is just simply write a new fraction where you break it up into a radical on top and a radical on bottom. And you're kind of like doing two baby problems as part of your fraction. So it's the square root of negative 45 on top over the square root of 36 on bottom. And you deal with them separately. So do everything we've already talked about in the top and then in the bottom. Separately from each other, when you pull stuff out, it's not going to get multiplied back together. Think about the numerator being separate from the denominator. They're not part of the same thing. So this would give me negative 1 times 9 times 5. The bottom is a perfect square, so it's just 6. And then I bring an I out for the negative 1, a 3 out for the 9. So I have 3I rad 5 over 6. And I saw this on a lot of your papers, and that's good math, but it's not done. It's not simplified all the way. The 3 and the 6, right? The 3 and the 6 are both outside the radical, so they go together. What is 3/6 simplified? 1/2. You're welcome to write that like this. 1I rad 5 over 2. I would write it like this. I rad 5 over 2. And you can write the I on the right side of your radical. I generally don't because it can be confusing sometimes if it's under the radical or not. So I just put it out front. But either way is correct. And then try the next fraction, please. Okay, so you begin by making your one radical into two different ones, a numerator one, a denominator one. So you had 7I on top, 5 radical 3 on the bottom. I saw this on most of your papers, but do you remember why we're not done here? What don't we like about this fraction in the math world? Do you remember? There's a radical on the bottom. Is that what you're going to say? There's a radical on the bottom. So here's the thing about radicals in the bottom. This number, radical 3, doesn't simplify, right? What class of numbers did we put that in when we were doing the sets? Irrational. Okay. What's true about the decimals on irrational numbers? They never repeat and they never stop. And so if you're trying to divide by a number where the decimal never stops, it's hard to do that division. And so years ago, before we had fancy computers that could fancily compute stuff for us, if people were trying to do that by hand from like a table of values or something, it was hard. It was easier if you could get the radical out of the bottom. This process is called rationalizing the denominator, meaning you take it from an irrational form to a rational form. And the way we would do that, does anybody remember? You multiply the top by something and the bottom. The same thing. What's that thing going to be? square root of 3. Okay. And the reason why and I'll show you how that's going to work. And the reason why you have to do it to the bottom and the top, we know why we have to do it to the bottom. Here's why. It gets rid of the radical. Because this is square root of 3 times square root of 3, which is the square root of 9. And what is the square root of 9? 3. And in a second, you'll see the radical will drop away. But the reason why we have to do it to the top is because if I only did it to the bottom, I've changed the value of the blue stuff. But when I do it to the bottom and the top, I haven't changed the value, I've only changed the form of the number. Because what's anything divided by itself? What's the value of it? 1. And so really I'm taking the blue stuff times 1. And so I haven't changed what it equals or what its value is. And so multiplying across the top like that gives me 7i rad 3. Okay, further simplifying that bottom, this really means 5 times 3 right here, which is 15. So the final answer is 7i rad 3 over 15. Okay, so that would be easy to divide by 15. Whereas it wouldn't have been easy dividing by the rad. And the reason why we still keep this convention of doing that, even though now we have our fancy computers, is just so that everyone in the world is using the same form of the number. Just to keep for consistency, really. Okay, does anybody need this up anymore? That process is called rationalizing the denominator. Oh, I had this on here. A little brain break before we go to the next part of your notes. It's a pie chart made from pie. So it says the most accurate pie chart ever. This is the pie I have eaten, and this is the pie I have not yet eaten. And I love it. It's the funniest thing ever. My best friend tagged this to me on Facebook because she knew I would love it, and I did indeed love it so much I had to share it with you all. It's great. All right, complex numbers. Complex numbers have a real part A and an imaginary part BI. Let me just get this out of the way so you can see. So when we were classifying real numbers, we had the set of rational numbers and the set of irrational numbers, and that made one bigger set of what numbers? The irrationals plus the rationals, the reals, okay? So today, we took our real numbers, we practiced with imaginary numbers, and those two sets make an even bigger set that we call complex numbers. And that set represents any number that we were going to work with this year, real and or imaginary. The standard form for any of those numbers is right here, the A plus BI. So what we're going to do now is still some simplifying of radicals, but then we're going to write them in this form and identify the A part and the B part. So briefly right here in words, to write a complex number in standard form, rewrite your expression, replacing any negatives with i's. Okay, we got that skill down. We've been doing that all class period. If your entire expression is a fraction, rewrite it as 2 fractions. Please highlight this part. That's not a highlighter. Rewrite it as 2 fractions with the same denominator so you can simplify. So going back to the I will statement right here, 5 plus rad negative 250 over 10, this is what that step 2 is talking about. Okay? If your entire expression is a fraction, rewrite it as 2. And I'm going to show you what that means in sort of a baby example. Just so you know where I'm coming from here. If we had these 2 fractions, how would you do that math? What would you say that is? The next step would be what? Add across the, which side? The top, right? But what happens to the bottom? Stays the same when you're adding fractions, right? This becomes basically 2 plus 4 over 3. Those are equivalent things. You can also do this backwards. If you started with the 2 plus 4 over 3, you could break it up into two separate fractions that have the same denominator. That 2 gets the 3, that 4 gets the 3. Okay. And this is what we're going to do with stuff that looks like this I will statement. Okay? It's just that instead of 4, we have a radical. But we can still break it up in this exact same manner. And that will help us write it in this standard form, which is our goal. So, here. This is a two-part thing. The first part is to write the complex number in standard form. And the second part is to identify the values of A and B. So that first one is a fraction. Please just give me your eyes and your ears for a moment so I can tell you what you are not going to do on this problem. This is bad. Bad. Don't do that. The reason why you can't do that is because of this plus right here. Okay? If there was no plus there, you could do it. You can only simplify fractions like that when everything is being multiplied, when they're factors. But the addition mucks it up for you, okay? So you can't do that. What you're going to do instead is the thing we just highlighted here. Rewrite it as two fractions with the same denominator. And here's how that will begin. This, you make one fraction with the 4 over 2 and one fraction with the radical over 2. And you work those separate from each other. So take a second and simplify those things. So 4 over 2 is 2. And then negative 20 is negative 1 times 4 times 5. The two things that I can simplify under that radical are the negative 1 and the 2. So this comes out as I, this comes out as 2. So I've got my 2 up front. I take this 2 times I times the 3 in front of that radical is 6I, with 5 left over underneath and 2 here. And then what is 6 divided by 2? There. 3. So I have 2 plus 3I, radical 5. Some common mistakes I've been seeing today are people doing 2 plus 3, which is 5, or 2 times 3, which is 6. You can't add these two things because they're not like terms. If 2 had a radical 5 or 2I, you could do that math on it, but they're not like terms, so you have to just leave them separate. Okay, and this was just part 1 of the problem. Part 2 asks to identify the A and the B parts. And here's what that means. So we talked about how a complex number in standard form is A plus BI. What part of this number is in the position of the A? 2. So I would say A equals 2. Did I do something wrong? So tell me your question again. I feel like I agreed with everything you said, so then I was unsure where your question is. What is your answer? Did you do 2 plus 3 right here? Okay, so that we can't do because this 3 is connected with the radical and 2 is not. So it's kind of like the same way I wouldn't do 2 plus 3x, because they're not like terms. I would just leave it 2 plus 3x. I could add 2x plus 3x, because those would be like terms. Same thing here. In order to do this 2 plus that 3, the 2 would have to have the exact same radical attached to it. Did that help you? So then when it asks for the b part, please notice something here in the standard form. B is the coefficient of I. It does not include I. It's whatever is being multiplied by I. What is that here? What is I times by? 3 radical 5. So it's the coefficient. And while that might seem like a completely useless skill to write in standard form and figure out what A and B are, in physics, now I don't remember my physics all that well, but I do remember that vectors are written in this form. Is it force and, no, it's distance and velocity. I don't remember what it is. Distance and velocity? I don't recall for vectors. But they're written in this form, and it's a skill to be able to read off the coefficients, the A part and the B part. So it's not a completely random thing that we're asking you to do here. Although there's no context for it, so it is kind of right. You tried that one. Try part B. The 36 comes out as 6. So now I have 3 halves minus 6i radical 2 over 4. And then that 6/4 simplifies again to 3 halves. So that's just the first part of the problem. The second part is to identify A and B. What's an A spot? Yes. Oh, thank you so much. So what's an A spot? 3 halves. B is everything being multiplied by I. So it's the entire second term, just don't write the I down. So 3 radical 2 over 2. The very last thing I do need to talk about before I let you go on the notes. It is negative. Thank you. That last section you have there, I'm only going to talk about those first 2. This negative 2 right here, bless you. How many i's do you see in that negative 2? None. How do we write none? So to write this in A plus BI form would look like this, quite literally 0 i's. And then your A would be negative 2 and your B would be 0. What's 0 on the B example? Which part, A or BI? The A, right? So there's no A. So we say that 0, so A is 0, B is negative 4.